So, so before starting today's class, I will briefly explain the following schedule of this course. So, in the next class, we will take the exam. So, so this is the offline exam. So you need to show up during the exam. Unfortunately, okay. Not unfortunately, so now I can see your faces during the exam. Also, this exam is the open book exam. So, and then the exam will cover what we learned during this course. So, just to review what you learned during the previous classes, and I think that's enough. And then this course is the English course, so the exam problem will be written in English, but you can write your answers in Korean or English, okay? And then after that, so the next week I will post some paper list that is related. Those are related to the some storage researches, such as the FTL implementation and file system and storage processing. So, and then for the next 3 weeks, you will be requested to read the research papers and then introduce the topics of the research papers during the classes, okay? And then also for this course requires the final project. And then, so I will explain about some tools. So it's the architectural simulation tool regarding the storage research. And then, so I will also explain about the final project of this course. So actually, I will post some detailed content about the exam or final project on the on the Blackboard. So okay. So the today's class, I will introduce some research work regarding the near data processing in storage systems. So this research is based on some dynamic near data processing framework working on the SSD, and which was presented in Micro 2017. And then after that, so I will introduce some architectural simulation tools related to the storage systems, and then you will be requested to use you will be requested to perform your final project using one of these architectural simulation tools. Okay. So in the previous class, I introduced some research work that performs the computation in FTL. So we learned why FTL is required in the SSD, and then FTL is required because the flash memory, so which is the main storage media in SSD, but flash memory has its own unique characteristics, and then in order to support these flash memories, then we need the FTL, that means the flash translation layer. And the flash translation layer performs some 3 major functions that manage the flash memory. So the address translation and garbage collection and where labeling. These FTL functions are very critical for the performance of SSD. So that means the storage system. So implementing very smart and very good flash translation layer firmware is very critical for the performance or reliability or cost lifetime of the SSD. And then in the previous, so actually we focused on the address translation functions in flash translation layer. So it is because this address translation is a critical function in SSD. So I explained why address translation is required in the SSD, and then based on the applied algorithms in this flash translation, then we can know the performance of the SSD can vary. Okay. And then in the previous class, I introduced some research works that utilize the computation ability in this flash translation layer. So instead of using flash translation layer for address translation, this research work exploit the computation ability in this flash translation layer. Also, we can note that this address translation function or some flash management functions in flash translation layer FTL use some data structures or some software functions. So if we can modify these data structures or some software functions in FTL, then we can do more things. Okay, we can apply we can apply some smarter SSD, and then this smart SSD can help the system improve the performance of entire systems. Also, we can apply this kind of smart SSD for some specific domain of applications, and then actually it is very important for recent researches. It is because actually it's not very difficult to improve the overall performance of computer systems. It is big, and then actually this performance improvement of the computer system is so that means that the overall performance improvement in the computer system is benefit from some advanced in semiconductor technology. So that means if we apply the better semiconductor technology, such as the narrow channel length or some smaller transistor size, then we can obviously improve the performance of computer systems. So if we apply the better semiconductor technology on the computer system, then the performance is improved. And then another benefit is that the power consumption. But recently, so as you know, the Moore's law is ending. And then also the Dennard scaling is already ended. So it is very difficult. So it is very difficult to use better transistors or better semiconductor technologies. So that means it is very difficult to improve the overall performance of computer systems. So instead, we can just focus on some specific domains of software or applications. So in the previous class, so I introduced the Graph SSD. So Graph SSD is designed to improve the performance of graph domain applications. So it's a specific domain, not the entire application, entire general purpose applications. But it is valid for and then it is a good research work because graph applications are widely used. And then if we can improve the performance of these graph applications, then it's okay. So Graph SSD will not be good for some other domains of applications, but if we can just improve the performance of some specific domain of application, that's enough. And then if this specific domain of applications are widely used in server systems or mobile systems or in our not personal, actually server systems or mobile systems, not personal use. So, and then that's valid for some good research work. Okay, so the research trend is it's changing recently, so that's okay. So, and then also the second work of the previous class was the index structure, and then actually index structures are widely used in database management systems. So that's also some specific domains of application, not the entire systems, but that's enough because these database management systems are widely used in server systems. Also the industry, like some companies also rely on the performance of these database systems, such to think about some what's the e-commerces. So e-commerces like Amazon or some Coupang in Korea also use the very strong database systems. Okay, so that's it. That's good. So if we can improve the performance of database management systems, and it's good for some research work. Okay, so now I will introduce the near data processing in storage systems. So, so I believe some students already know about the near data processing, and then I also frequently talked about this near data processing in other seminars or some presentations. Okay, and then actually near data processing is very popular recently because also we are handling big data applications. And then so I will briefly also explain about the big data application, why big data application is critical, and then why big data application is changing the recent architectural research in the computer systems. Okay. Okay, so let's think about some conventional systems and near data processing. And then what's the conventional systems? So conventional systems means that conventional systems mean that so it's what you learned in undergraduate or in the graduate courses. So think about the computer architecture course for undergraduate student or advanced computer architecture course for graduate student. So what did you learn? We learned about the architecture of a processor. Also, we learned about the memory hierarchy. And then in the advanced computer architecture course, we learned about the advanced process architecture, such as out of order processing, or speculative execution, superscalar, also some other specific architectures such as VLIW, very long instruction word, or vector processing, and SIMD or SIMT architectures. So those are just handles the process architecture. So and then another important topics of this computer architecture courses is memory systems. So in the memory systems, we learned about the memory hierarchy, and then for the multi-core systems, we learned about the memory coherency or memory consistency of these multi-core systems. Okay, so if we just focus on the conventional systems, then these conventional systems are composed of process architecture and memory systems. So here is the process architecture, and then memory systems are here, and then this is the processor. So what is the main purpose or main goal of this processor architecture research? So main goal or main purpose. The first goal of the process architecture research is performance and cost. So in the process architecture research, we focus on the performance of our processing engines, and then the cost, that means the power consumption or energy consumption of this processor. How about the memory? So we assume that our all data is stored in memory systems. So actually the performance is very important, but performance of the memory system represents the latency or bandwidth. So latency means some required cycles for fetching or moving data from the memory systems to processors. Okay. Also, if we just focus on the coherence or consistency of the memory systems, so it also the important topic of that is coherence or consistency is the performance and how to handle some strict rule or some loose the rule in the memory coherence or consistency protocols. Okay, and then, but the basic structure, the basic architectural rule of this memory system is memory hierarchy. So from the very early computer architecture or from the very early computer systems, and then also until today's or recent computer systems, we exploit memory hierarchy. So it is because there is no perfect memories. There are no perfect memories. So what is the perfect memory? It's the cheap, fast, also the dense. So that means density is high. But we cannot use those kind of memories. So we apply the memory hierarchy in order to exploit the data locality of the application, the software. So the all kind of applications, this data locality is frequently observed. And then if our computer system computer systems are designed for exploiting this data locality. So especially memory hierarchy is designed for exploiting data locality. So data, this is very important. Data moves from low level to high level memories. So data moves from the low level memory, and then this data is moved to the higher level. And then on the top of the higher level memory, what the processor is on the top of this higher level memories. So data moves from the low level to the higher level. It will take cycles. But we can observe that the data inside of the higher level memories are frequently accessed by processors because of data locality. But why do we need near data processing? So what is the meaning of the near data processing? That means that the processing engine locates near data. Okay. So this is the traditional model. So processor is here and the memory is here with some levels of hierarchy. Then the data moves to this processing engine, and because so actually every application requires to process our user data. So data moves from low level to the higher level because processing engine is located on the top of the high level memories. But near data processing means that this processing engine is located near low level memories because this data movement time or data movement cost is very high for modern systems. So why do I mention modern systems? Because the modern applications require a large amount of data. So that's why modern applications are frequently called big data applications. But actually, we call our the current era is the big data era. So processing engine is located near low-level memories, and then instead of moving this data to this main processing engine, data is processed by this Geodata processing engines. Okay, so with this Geodata processing, we can reduce the data movement cost. That is the required time or required cycles for moving data from low-level memory to the higher-level memory. So why do we need NDP, Geodata processing? Because we need to handle big data applications. So that means the applications are changing, and then as applications are changing, so we can apply some modified, enhanced architecture to our computer systems. Okay, so let's talk about the big data. So what is big data? We frequently use terminology big data. So big data means that data sets that are too large or complex for traditional data processing application to adequately deal with. It's the meaning of the big data that can be found in Wikipedia. So, this definition of the big data, I can focus on the too large or complex. So that is the characteristics of big data. And then why this is too large or complex, and what are the issues or what are the problems of this too large or complex data. The issue is that if this big data is handled by traditional data processing systems, then the performance, that means the performance efficiency will be very low, because with these traditional systems, actually I talked about the conventional systems. So, and then I mentioned these conventional systems, then it is because I need to explain why conventional systems are designed with the memory hierarchy or some different process architectures. But with these conventional systems, big data applications are not, the performance of the big data application is very low. That means that the efficiency is very low. So with these conventional systems, it's not good process big data applications. So that's the problem. But we use big data applications very widely. So big data applications are widely used for social networking services, which are very popular recently, like Facebook or Instagram. It's called the SNS. And then, so these big data applications are used for internet analysis or social sciences, and then data analytics, like database systems. Also, so for the biomedical systems, we frequently use the big data applications. So what is the feature of the big data application? The data size is very large. And then for this, in order to process this large data, then the efficiency of the conventional system is not good. So for the big data applications, we need the high performance data processing system. So, and then for this purpose, we can apply the massively parallel processors such as GPUs, graphics processing units, or we can design some specific accelerators for big data applications, such as the Google TPU. So Google TPU is designed for processing neural network applications. Okay, and then advanced memory systems. So because this large amount of data is stored in the memory systems, the performance of the memory systems are also critical. So what kind of memory is required? So it's a perfect memory, such as higher density, low access latency, and higher data bandwidth. So so recently the DDR5 is applied to the modern computer systems. And then what is the main features? What are the main features of DDR5? Actually, the main feature of the DDR5 is the higher data bandwidth. Why do we need this higher data bandwidth in the memory systems? It's because with this advanced memory systems, we can reduce the data movement cost in the computer systems, and then the overall performance can be improved. Okay, so this is but these are some traditional approaches like higher performance data processing, the advanced memory system. So this is the actually computer architect have worked for these high performance data processing engines or advanced memory systems. So let's talk about the memory hierarchy. This is the very basic concept. So this is some shape of the memory hierarchy. So you can find that the register file is on the top of the memory hierarchy. And then what is the feature of this register file? It's a high cost, very expensive, and high performance, low capacity. So we know that the size of the register file is very, very small. But why do we need the register file? Because register file is located, right? Register file locates very inside of the processor core. So that means that RF, the register file, is the closest memory component, and it's closest to processing engines. The processing engine is here. Processing engines are near register file. But so register file is very fast, and then the size is very small, but it's okay because of data locality. But large amount of user data is stored in the storage systems like SSDs or HDDs. This is because the density of this SSD or HDD is very high, and then so it's low cost. But how about the performance? Performance is also very low. But high capacity or some non-volatile so persistence is the why. So we use these storage systems in order to support the high capacity and the persistence of the data. Okay, for data. So as I explained, computer unit is near register file. So in order to use these processing engines or computing units, then data should be moved from the low level, from the storage to this register file, like so near processing engines. So if the data inside of the register file or low level cache is frequently used, then we can reduce this amount of data movement in the computer systems. But so I explained about the definition of the big data. So data size is very large, or data structures are very complex. So this data locality data locality observed in conventional applications are not applied to big data applications. So that means that the miss rate, so for example, the miss rate in the cache memories are very high for the big data applications. So, which means these cache memories or main memories are not efficiently used by big data applications. This is another feature of the big data application. Also, as the data size is very large, the data movement cost is also very high. So instead, cost for data is very critical for the big data applications. So because of these issues, and then so in order to solve this, in order to handle this very high data movement cost, we can apply the neo data processing. But also this neo data processing for storage system is called in-storage computing. So I like ISC because the computing units locates between storage and main memory. So because, and then, so we, in the first class of this course, we learned how storage systems are connected to host systems. So actually, in the conventional systems, this is CPU, and then CPU is connected to the main memory with a very high bandwidth memory bus. So this is a very high bandwidth. But you know, the storage system is connected to CPU via external bus, external interconnection bus such as SATA, PCIe. So recently, the bandwidth of this PCI is also very high, but it's extremely low compared to this memory bus. You know, so what's the problem? If this storage system, the data inside of storage system is frequently accessed by host CPUs, then the data transfer time between the host system and then storage system will be dominated. Okay, so that will occupy the large portion of the some execution time of the entire execution time of the big data applications. So in order to reduce this high data movement cost, we can apply the in-storage computing. So that means that the computing units locate inside of the storage system or near storage systems. This is the idea of in-storage computing. So I will explain in-storage computing for near data processing. So this near data processing can be applied using in-storage computation. So actually this in-storage computation is not a new idea. So if you see the year published the year of this example papers, then you can find, oh, these papers were published in 1998. It's about more than 30 years ago. From it's about more than 30 years ago. So it's a very old idea, not a new idea. And then this idea is applied to hard disk drives, because at the time, the hard disk drives are the main storage systems in the computer systems. So if you are interested, then you can read these papers like active disk, active storage, and intelligent disks. So in these papers, the authors present the benefit of in-storage computation. So which means the processing engine processing engines like CPUs are applied to the storage system like HDD actually. And then if the data is processed by these storage processors, then the authors states that the performance of the some applications can be improved. Right? And then actually this is obvious. Instead of moving the large amount of data to the host CPUs, then if this data is processed by storage processors, then we can reduce this data movement cost, then we can improve the performance of some applications. Okay, and then that's obvious. But if you read this paper, then you can find that this paper applies some host CPU like processors. So that means that some Intel CPUs or Intel CPUs, that is the host CPU. The authors assume that the host CPUs can be applied to these storage systems. But so actually we can know that the host CPUs cannot be applied to these storage systems because of many issues such as thermal issues or power consumption issues. So this is the idea work, but recently the performance of the ARM processor, like embedded processor, is also very high. And then so also if we apply SSD, the flash unlike the hard disk platters in the HDD, the flash memory in SSD can support some constant latency from the data read. It's not exactly constant, but nearly constant. So now SSD, so we can apply the in-storage computation and then more effectively. Okay, that's why in-storage computation is somewhat popular in our research community. Okay, so the conventional storage system. So conventional storage is the cheap passive devices. That means that and then as I explained, the storage system is just the IO devices, and then the host systems just send the read, write, or erase commands to these storage systems, and then that's enough. So because the storage system is done, actually that means actually storage system is just the memory, and then the large amount of data, so the large amount of user data is just stored in the storage systems. And then for the host system, this storage system is just a block-based memory, and then host system just sends the very simple IO commands like read, write, erase. Then another feature of this conventional storage system is that it's very slow, and then it's a passive device, and then long seek time and high latency. So we learned about the hard disk drive architecture, but what's the problem? So data size is very large recently. The high volumes of data is stored in this large, there's also this very large storage systems. So it's slow, and then slower, and then much slower. Okay, because the data size is very large. So we can say that data movement. So actually, the computer architect focus on performance of processing engines. It is because it's very critical for the performance of computer systems. So in order to improve the performance of computer systems, what do you do? So we can buy better processors, like better Intel CPUs, and then we can change these Intel CPUs in our desktop computers or supercomputers. Or we can buy better GPUs for some parallel applications or machine learning applications. So our so we can think that if we just change, or if we just improve the host CPUs or host processing engines, then we can improve the performance of entire systems. But data movement is now very critical for performance. The data, and then data movement between storage and this CPU host processors is very, very critical. Okay, is because so these data stored in the storage system are frequently accessed. So then recently we can use the SSD, and then recently instead of SATA, we use the NVMe based SSD. Okay? So NVMe based SSD exploits the PCIe interconnection bus. So you know the PCIe is support the higher bandwidth compared to the SATA, and then also with this PCIe, then we can just apply some software based driver for the storage for the storage systems like SSD. So that means PCI. So in order to support this SSD, then we can apply the NVMe based storage SSD. So NVMe is NVMe is just the protocol between CPU and this SSD. So this is a software-based protocol. So that means we can easily modify this software-based NVMe protocol. Okay. And then as I explained, this is the typical structure of the SSD. And you can find that this is the SSD processor, then DRAM, and then the flash packages. So this is the complete system. The processor is here, main memory is here, and then actually the storage is it's a persistent memory is here. So if we just see the structure of SSD, then SSD is just a complete computer systems. So what's the benefit? Using this SSD processor, so actually the SSD processor is required to run formula. So that means that SSD processor is just a general purpose processor. So like it's very similar to CPU of our host system. So we can apply this computation ideas using SSD processor, and also we can exploit the DRAM space as the main memory space for this computation system. And then how about the storage? This is the very large storage, you know. So we can use the storage space in NAND flash packages or NAND flash memories. So that means we can use SSD as active storage systems. So that means the data can be actively processed inside of SSD. That is the storage computation idea. Okay, so I will introduce the research work called, so that represent the dynamic near data processing in SSD. Okay, so I explained about the near data processing. Also, I also explained the advantage in near data processing. So with the near data processing, the storage system has the storage processor, and this is the general storage processor, and then this is the some the processing thread. So that means that the some computation part, the computation kernel in, so actually in the conventional system, this computation kernel is executed by host CPUs, but this computation kernel can be offloaded to the storage processor. Okay, so this is actually the user code. Okay, so this is a user computation kernel, compute kernel, and then the large amount of data can be processed by this compute kernel by storage processor, and then the size of the data can be reduced. Okay, and then if this small size of data is transferred to the CPU, then the bandwidth of the storage interface is very low compared to the bandwidth of this memory, the bandwidth of the main memory. So that means we can reduce the data transfer time from storage to host systems. Okay. So without NDP, this is some entire execution time of a certain application. This entire execution time is composed of data computation time at host processor, by host systems, and then this is the data transfer time from storage. So this is some data transfer time in the external bus, external interfaces such as SATA or PCIe, or also we require some internal data transfer time inside of the SSD or storage system. So it is also critical. Okay. So if you see this execution time of a certain application, you can find that so I also so this data transfer time is very long. Okay. So it's very similar. It's similar to the data computation time by host processors. But if we apply near data processing for this application, then the data computation time by host processor can be reduced because some computation is done by this storage processor. So this host computation time can be reduced. Also, external, the data transfer time by external storage interfaces can be also reduced because the data size transferred to the host system is also reduced. And then actually the internal transfer time is the same. So internal transfer time is that the data transfer time inside of the SSD here. So, but the size of data accessed by this computation kernel is the same inside of the SSD. So internal data transfer time is the same. And then this data computation time inside of the SSD is included, this newly included with the NDP. And so this data is processed by internal storage processor. This time is newly added. And then for the entire execution time includes the data computation at host, and then external data transfer time, then in data computation time at storage, and then the data transfer from storage. And then if the sum of this time is less than this without NDP cases, then we can improve the performance. That's so it's a good idea. So, but it depends on applications. So it depends on so we can apply some parallel processing for some different data, but if this parallel processing is not possible, then this data computation time is just applied. And then when I explain about the NDP, so I assume that this scenario, so So storage processor is here, and then actually this large amount of data is processed by CPU. And then we assume that, I assume that this large amount of data is processed by CPU, and then for a certain step, the data is processed, and then the data size is reduced, and then based on some other steps of the CPU processing, this data is processed again and again. But it's just sequentially, okay? But it depends on applications, okay? Okay, so it's a good point. But usually if we just analyze some applications, some tasks the tasks to be executed sequentially. Okay. So, but due to the cost issue, the SSD used a very cheap real-time ARM processor. So due to the cost issue, the computation ability of this storage processor is very low. So, and then also, why do we need storage processors? These storage processors are used for FTL functions such as garbage collection and ware labeling. And then, so actually the address translation is required very frequently, but the garbage collection or ware labeling is performed by the storage processor occasionally. So sometimes this garbage collection or ware labeling, for this garbage collection or ware labeling, the storage processor need to consume the large amount of computation time, but it's occasionally, not frequently. So what's the problem? The available computation resources in this storage processor can vary, like it's vary. Okay. So the storage processor cannot support very stable computational resources with the computational ability for near data processing. So what's the problem? This data computation time by storage is very long, then overall execution time can be increased by near data processing. Then the entire performance can be degraded. Okay, so this graph, this slide shows this case. Okay, so I summarized the obstacles in storage processing. So it's also the computation power is very low for the embedded processor, and then the available computation resources vary dynamically. So dynamic computation resource availability, and then so actually in the previous work, researchers apply near data processing manually. So that means that, so this is the workload, and then the researchers just split this workload to some host processing part and then SSD processing part. And then this SSD processing part is manually applied for near data processing. And then this host part is done by host processor, but the workload is divided manually. But this is very difficult. So we don't know the available computation resources in SSD. So, and then this is dynamically changes. So this manual workload partitioning is very, very difficult. So this is the summarizer. So it's the name of the paper. So this in the summarizer, the researchers applied the dynamic near data processing framework. Okay. So actually, the concept is very simple. So the summarizer monitors the available resources in SSD, and then if the SSD has some enough resources for in SSD computation, then near data processing is just applied. Okay, so computation kernel is executed by storage processors, and then the near data NDP is just applied. Then storage can send a very small size of data to the host. But the storage processor does not have enough computation resources for near data processing. Then near data processing, if we just apply the near data processing for this case, then the execution time will be, it can be longer. Okay, not so execution time can be increased. So in this case, the near data processing is not applied. The entire data is transferred to the host system. So you know this host CPU is beefy. That means the performance is very high. So because this large amount of data can be processed by these host CPUs, but so you know the data transfer time can be long, but we can exploit the high computation ability of the host CPUs. So this is the dynamic near data processing concept. And then for this purpose, we apply the summarizer framework inside. So we modify the FTL firmware that in the SSD. So this slide shows the architecture of the summarizer. So actually you will be very familiar with this figure because I just showed this part in the previous class. Okay, this is the typical architecture of the SSD, like this host CPU, and then this is the NVMe host driver, and then the NVMe host driver is just a software that use the PCIe bus. And then so the host memory, the data structure is managed, and then also you can find the SSD firmware is here, FTL is here, and flash, and then SSD DRAM. So, and then for this dynamic near data processing, this summarizer part is added to the SSD firmware. So this is software part. So the summarizer communicates with the flash translation layer of the SSD firmware. So a summarizer has the task controller and then task queue, and then also there's some user function space. So this is the SSD firmware. So this part is executed by SSD embedded processors. And then let's see how summarizer works for dynamic near data processing. So summarizer has 3 steps. So initialization step, and then processing step, and then finalization step. And then these steps are required for dynamic NDP. So let's see the initialization step. So in the initialization step, the user function should be uploaded to the SSD. So this is the user function part. So during the initialization step, the user just stored this user function in the main memory, and then by the modified, this is the modified NVMe command. So this modified NVMe command called init, and then this command has the pointer for this user function. So if this command is given to the this system, then based by the modified NVMe protocol, this user function is offloaded to the main memory. It's the memory, the DRAM of the SSD. Okay, the function is offloaded by this new NVMe command, and then this offloaded function is registered in the summarizer. So this function is registered, and then also the summarizer manages the pointer for this offloaded user function. Okay, this is the initialization step of the summarizer. Then it means the Geodata processing framework. And then let's see how the Geodata processing is performed by summarizer. So also we modify the NVMe protocol, and then new NVMe command is added. So this command is called the read and track. So that means, as you can see, this is the read and processing. And then actually for the read command, we just provide the logical block address, but this read and proc command just provides the logical block address and then function pointer. So this is the pointer for offloaded function. So if okay, so if command is given to the SSD based by this IO controller, and then as you know, the LBA is just translated into PPA inside of the SSD. This is the address translation in the SSD, and then the SSD generates the NAND flash command based on the required PPA, the physical page address, and then this command is given to the flash memory, and then page data is read from the flash memory. This read page data is buffered, so that means it's stored in the main memory of the SSD, and then because this data is buffered in the SSD, then the response for this NAND flash command is given to the SSD firmware. So this is the response queue, this is the request queue. So if this response for requested page is given to the SSD firmware, this information is given to the task controller of the summarizer. And then summarizer check the task queue. And then if the task queue has the empty entry, then summarizer registers this task to in the task queue. Like with this is the address for the buffered page data, and then this is the pointer for offloaded function. And then summarizer just returns the special completion code. So actually in the normal mode, the page data is transferred to the host memory with the DMA protocol. And then if the transfer is done, then completion code is registered in the completion queue on the host system. But with the summarizer framework, this page data will be processed by this summarizer frame. That means the processed by SSD processor. So instead of transferring page data to the host memory, the summarizer just returns special completion code to the host memory. And then this case shows when the task queue is full. So that means that the computation resources in SSD are occupied by other tasks, like some FTL functions or other Geodata processing functions. So if the TQ is full, the task queue is full, then summarizer just returns the normal completion code. In this case, the page data is returned to the host CPU. So this page data can be processed by BF host CPUs. This is the dynamic computation mode. And then finalization. So with this dynamic geodata processing, some data is processed by SSD processors, or another part of the data is processed by host CPUs. So we need to merge these data processed by host CPU and then data processed by SSD processors. So the finalization step, also we apply the new NVMe command called final, and then this NVMe command also send the function pointer for this offloaded function, and then this function pointer is given. Summarizer returns the result, that is the partial result done by SSD processors, and this result is returned to the host memory, and then host memory performs the merge operation for the result by host CPUs and then result by SSD processor. So this slide summarize actually, okay. This slide shows the summarized steps for summarizer. Okay, so initialization step, computation step, and then finalization step. Okay, and then required NVMe comment here. So for this summarizer work, we used also the real SSD development board, and then we evaluate the effectiveness of the dynamic geodata processing. So this development board is composed of general ARM processor is here, and then FPGA part, and then also the NAND flash interface is implemented by this FPGA part, and then we used this ARM cores for geodata processing. And then also this is the also main contribution of this paper. So usually in the computer architecture work, we can use the software architectural simulator, but the problem is that the software architectural simulator cannot reflect every hardware aspect, cannot reflect every hardware aspect. So that means that the performance by this software architecture can be different from some real hardware performance. That's the problem. But we evaluate this geodata processing ideas using a real SSD development board. So that is another contribution of this summarizer work. Okay, so this detailed photo. You can find the ARM processor and then the flash DIMMs connected to the Altera FPGA. This graph shows the performance by summarizer, and then it is the performance, the execution time of the TPC H carry 6. Then, as you can see, this x-axis means the static workload offloading. So that means that the workload is partitioned by static ratio, like 0, 0.2, 0.4, something like that. So 0 means that this is the CPU only processing, and then this is also baseline. So entire data, data is processed by CPU, host CPUs. And then 1 means that the SSD only processing. So it's ridiculous because the computation ability of the SSD processor is very low compared to the host CPU, but we can apply the SSD only processing because it's a dynamic geodata processing. So that means the entire data is processed by SSD processors. And then this is dynamic, means that this is a dynamic geodata processing by summarizer. And then SSD time means the SSD processing time and data transfer time. So it's the internal transfer time, external transfer time, and the in SSD processing time. Host time means the host CPU processing time. Okay, and then this is the execution time normalized to baseline. So CPU only. So you can find that when the near dynamic near data processing is applied by summarizer, the performance can be improved. That means the execution time is decreased. So if you see the detailed ratio, so you can find that with the CPU only, the SS time is the 0.7. So you can find that the SS time is very large for this benchmark. And then CPU processing time is just 0.3. And the NDP is dynamic NDP is applied. This SS time and then CPU time is also reduced by 0.6 and 0.24 respectively. So this is what I introduced in the first page of the summarizer. So with the NDP, that we can reduce the execution time of the application because this host time is reduced, and then also the SSD part. This part is also reduced. But I said it's ridiculous. But if every data is performed by SSD processor, then the performance is degraded. So it's very slow. But it's ridiculous. So, you know, the entire workload is done by SSD processor. So, but if we just apply the static uploading static partitioning, then the execution time can be reduced. That means the performance can be improved, but this ideal ratio of this data workload uploading varies by application and situation. So we cannot. It's very difficult to find. It's very difficult to find this ideal partitioning ratio. Okay. So we also tested the other applications right here. So you can find that. So the performance can be improved by dynamic near data processing. So if you see that this TPCH query 1 or string similarity join, then you can find that with the zero static partitioning, the performance is degraded. Sometimes it can be increased. Performance is improved, but for other applications, the static partitioning is not good for the near data processing. Okay. So also we test some design spaces for near data processing. So actually, the storage interface is the data transfer bottleneck. So you know, the bandwidth of this storage interface is very low compared to the memory bandwidth. And then because of this, so we assumed, so when we make the SSD, then we set the internal bandwidth is similar to the external bandwidth of the storage system. And that's obvious. It's like, so even though the internal bandwidth is very high compared to the external bandwidth, and then because of this external bandwidth, we cannot make use of this high internal bandwidth. Right, it's obvious because this is the bottleneck. It's like it's a very large load, so that has a large number of lanes. But after that, this load has a very small number of lanes, like this. So what's the problem? The resources of this the large number of lanes are just wasted because of this low bandwidth. So it's a small load. So usually when the SSD is designed, the internal bandwidth is similar to the external bandwidth of the storage interfaces. But we can apply the high internal bandwidth because the data can be processed by SSD processor, and then when the NDP is applied, then we can reduce the size of the data. So that means that we can, if we just increase the internal bandwidth, then we can more data can be given to this SSD processor, and then the data size is reduced, and then this data is just given to the storage interfaces. So that means that the storage interfaces are occupied by small amount of the data, but inside of the SSD, the large amount of the data is processed by storage processors. So we apply the higher internal bandwidth in the development board. So this is the one-to-one. So one-to-one means that this is the external bandwidth. Oops. And this is the internal bandwidth. So 1 to 2 means that the internal bandwidth is doubles. It's a double of the external bandwidth. And then we just measure the speed up by summarizer. So as you can see, if we just increase the internal bandwidth of the SSD, then if the near data processing is applied, then you can find that the speed up by near data processing is also increased. So that means that if we just increase the internal bandwidth of the storage system, and then near data processing is applied, then we can maximize the performance of the system. Okay, so we just increase the internal bandwidth. So the more data is handled by SSD processor. Okay. And then also we can apply the better SSD processor. Okay, because the price of the server CPU is very expensive, very high compared to the embedded processor. We also analyzed some cost effect. So we applied the high performance embedded processor such as the X1 performance, X2 performance, like this. So and then we also measure the speed up by near data processing, and then as you expected, then if we use the higher performance embedded processor for near data processing, the entire performance is also increased dramatically. Why is it important? And as I explained, the cost of the server CPU is very high, but the cost of the embedded processor is extremely low. So it's very cheap to increase the number of cores inside of this storage devices, because it's very cheap. But it's very, very hard. It's very expensive to increase the performance of a server CPUs. Okay, so we can invest more cores for the Intel Xeon server CPUs, but the price of the Intel Xeon CPU is more expensive if the CPU includes more cores. Okay, so server CPUs are very expensive, but embedded processors are very cheap. So if we just increase the performance of embedded processor by increasing the number of cores of the SSD processor, then we can benefit from near data processing more effectively. Okay. So this is the contribution of this work. we apply the dynamic geodata processing framework for SSD, and then also we apply the summarized programming model by changing the API and NVMe protocol of the SSD. So one student asked about how to increase the number of cores in this evaluation board. So actually, you know, this is the architecture of the evaluation board, and then actually this board this ARM core has many cores, like this. This ARM core has actually 8 cores, but the formula runs using this 1 core, and then actually for the geodata processing, we use only 1 core. Okay, but if we increase the number of cores for geodata processing, then we can increase the performance. So, you know, actually in this development board includes the multi-core ARM processors. And then for this result, we use only 1 core for the geodata processing, and then for this experiment, we use the multi-cores of embedded ARM processor like this here. Okay. Okay. So it's done. So I introduced the other NDP ideas for storage process in storage computation. So any questions? Okay. Okay. Let's take a break for 10 minutes. So I'll be back at 12:03, and then I will introduce about our term project. Okay. Let's take a break for 10 minutes. Okay, so in this time, I will introduce the 2 SSD architectural simulators, and then I will briefly explain about the project for this course. So, okay. So SSD has also architectural simulators. So this is the software that emulate the operations of SSD, like the computer architecture simulators such as GEM5 or GPGPU sims. And then we can categorize these SSD simulators as trace type simulators and then full system simulators. So trace type simulator means that, so as you know, in the first class, I explained the SSD is just IO devices. Oops. SSD is here. And then the SSD is connected to the host systems via storage interfaces. So host system just send IO commands such as read, write, or erase commands to the SSD. So if we just focus on the SSD part, the SSD receives the host commands like read, write, erase command with the logical block address, and then returns the data for read, and then also performs the write operations or erase operations inside of the SSD. So if we just capture these IO commands from host system, then we can run SSD part using these commands. So trace type simulators means that the thread type simulators just implement the operation of SSDs, and then these simulators receive the host command here, and then SSD performs the host commands, and then we just measure the performance or cost metrics such as power. Also, we just measure the number of erasures, write amplification by this SSD model. This is the trace type simulators. Sorry. And then full system simulators means that so actually this is SSD is the part of IO devices in the full system. And then the issue of the stress type simulator means that so actually the SSD returns data. So that means that the requested the data to the host system, and then the applications that is running on the host system receive the data and then do something with this data. So actually, the operation of the SSD is the interactions between host system and SSD operations. But with the trace type, host system just gives some commands to the SSD, and then this timing of the commands does not change. Timing of commands does not change based on the operations of SSD. But the application that runs on the host system are influenced by performance of SSD. So that means the commands from the host system can change by different operations from SSD. The full system simulator is just a full system operation using both full system simulators and SSD models. Okay. So how we introduce the one trace type simulators, and then one trace type simulator and one full system simulator. Okay, so the first one is the Eagle3 Ssd Simulator. So this is the trace type SSD simulator. So this Eagle3 simulator is developed by IT University Copenhagen and India. And then this is developed based on the Flash Sim. So this Eagle3 simulator implements the behavior of SSD using the SSD controller type and then flash memory arrays like this. And the SSD controller implements this address translation, IO scheduling, and then also other flash translation layer functions such as garbage collection and where labeling. Then also, this Eagle3 simulator also implements some workload generator. So workload generator generates some commands. That means required data or some operations based on some workload type, and then simple IO scheduler that exists in the operating system is also implemented. Okay, this is the Eagle3 simulator. So you can download Eagle3 simulator from this repository, and then you can also find the installation guide and the tutorials in this GitHub repository wiki. Okay, and this is the part of the demo code. Then if you see this demo code, then you can find some FTL design. So I believe the Eagle3 supports several FTL designs such as DFTL or page level, or it's a block level FTL. Then you can also adjust some several parameters for this SSD. So you can also define the workload like this here. So this is the Eagle3, and then also Eagle3 also reports the some performance of the SSD, like that is throughput by time. But this is the trace type simulator. Also, I will introduce simple SSD 2.0. So this is the some enhanced version of the simple SSD that support full system SSD simulation. And then actually this simple SSD 2.0 was presented during Micro 2018, I believe, 19. Oh, I forgot. So if you find this paper, the micro paper, that you can learn about the simple SSD 2.0. So also you can find the several full system simulators such as the CMix and the Mars X86. So these are the some full system simulator that support the operating systems or file systems, and that emulate operating systems or file systems, and then that with these full system simulators, you can measure the some behavior or some performance metrics of the some full system. Also very popular so very popular Gen 5 simulator also supports the full system mode. So you can use the Gen 5 for system core emulation mode. So that means some CPU architecture or DRAM operations can be simulated by Gen 5 system core emulation mode. Also, you can use Gen 5 for full system simulation mode, okay, like FS mode. So with this full system mode, like the what's that? Virtual systems of the virtual box, then you can attach some file system, and then you can run operating system with this full system mode Gen 5. It's very similar to the virtual system. It's very similar to virtual box, like virtual virtual systems. So I also explained about the trace-based simulation mode. So you can find the trace files here, and this trace file is given to the SSD model, and then we can measure the performance of the SSD. But in the real system, as I explained, this timing of the SSD commands can be influenced by performance of SSD, like behavior of SSD. So actually, in the real system, the host system interacts with I/O devices. So and then based on the response from I/O devices, the performance or some commands can be changed. So, but in the trace-based simulation, the I/O trace file is just provided to the SSD model. So, and then we cannot change this I/O trace file. So just the trace. Then, so we cannot measure the interaction between host systems and SSD models. So this slide shows the detailed architecture, detailed architecture model of the simple SSD 2.0. So actually this simple SSD 2.0 combines the Gen 5 full system mode and the NAND flash system, maybe. So another SSD architecture model. Okay. So also this SSD model implements the several layers such as the FTL and then flash layer, and then what is HIL? Yeah, so it's the host interface layer, and then the internal cache layer. I don't remember. Then also, so this simple SSD 2.0 model implements the several architectural model of the SSD. Okay. This simple SSD 2.0 can be downloaded from the GitHub repository right here. And then also you can find the very detailed document in this document site. Okay. I think the documentation of the simple SSD is very great. It's so great. Okay, so I will explain about the term project of this course. So goal of this term project is to explore SSD architecture. Okay, so that means that with these architectural simulators, you can configure your SSD with various parameters. Okay, and then by changing these parameters, you can measure some metrics from the this SSD simulators. So you can measure the IO statistics like input and output statistics or input and output performance metrics, or you can collect the power and energy consumption using this model. So actually, the simple SSD supports the simple SSD reports power and energy consumption using MacPad. So MacPad is also another architectural simulator that measures the power and estimate the power and energy consumption of the processor or memory models. Also, you can collect the instruction statistics, like the internal instructions inside of the SSD. Also, you can measure the FTS statistics, like the performance metrics or performance metrics by flash translation layer, like write time amplification, or number of arrays, some lifetime of the flash memory. Okay. Actually, for this term project, you can use any SSD architectural simulators, but I recommend to use simple SSD full system mode. So with this simple SSD full system mode, so you can configure the entire system, so host system also you can configure SSD, okay, with some parameters. So this is some example project steps. So you can configure simulators using the provided parameters by simulators. So you can configure SSD architecture models such as the firmware model and then flash memory topology. Like with the firmware model, you can configure the FTI algorithms, what size of data buffer and how the data buffer is managed. So you can configure you can change some parameters for these SSD architecture simulators. Also, you can configure the size of the flash memory and then topology, such as some number of packages or number of ways, number of planes inside of a flash memory. Okay, and then also you can configure the system model, like in the full system model of the simple SSD. So you can change the storage interfaces such as SATA or NVMe or UFS in the simple SSD. And then if you use the full system mode, then you can run the workload such as the storage benchmark, such as FIO is a flexible IO tester, and then this FIO. So you can find the FIO on your common Linux operating systems. And then if you just implement the full system mode using simple SSD, then you can run Linux operating system. That means you can also measure the performance of SSD using the normal application. So you can also execute the FIO it's a flexible I/O tester, and also you can measure the performance of SSD. So using the FIO, you can also generate the sequential command or some random commands. Then also you can compare the performance by various configurations of SSD. And then if you use the trace mode, then you can also use the existing SSD traces, such as the open storage trace, right? So you can get these traces from this site, okay? So you can collect some performance result or performance statistics or some cost statistics by design space. So like SSD configurations or system configurations, or just compare some performance or some consumption, energy or power consumption by various configurations. Okay. So this is the project schedule. So, and then next week we will take on the exam. So we will take only one exam for this course. So that's why this exam called the midterm exam. So we will take the midterm exam the next week, and then so I will receive the proposal submission. So this proposal submission, so to summarize the topic of your term project with the one-page document. So just one page. It's a very short proposal. And then, so actually the last day of this course is the December 21st, but at the time, I need to participate in some conference. I need to participate in the conference. So I will just, so we cannot have the class. So I will receive recorded video. So in this recorded video, so you need to record your presentation, and then also I will receive the project report. Okay, so by December 17th, you need to submit the recorded video, and then it's a recorded video is about the 5 to 6 minute length. Also submit the presentation slide in the recorded video. So you need to generate make the presentation slide also for this presentation. So also please submit the project report. Okay, so by December 17th, please submit recorded video. So and then presentation slides, and then project report. Okay, and then this is an individual project, so every student need to participate in the project. So this is an individual project, so it's a one per team. And then please present and write in English. So this is the English course, so please practice your presentation and then writing in English. Okay. Okay. So it's done. So any questions? Okay. So thank you for your attention, and then so next week we will meet in the real physical classroom. So structure. Okay. So actually, I will make several questions about what we learned in the previous classes. Like it's not related to some discussion. It's not related. It's not relate to writing some discussions or writing some your opinions for some aspect. So I will prepare some questions regarding some what we learned during the classes, such as what's the number of write by the file systems, what's the number of read by the specific file system. So what's the performance metric? So what is the number of erased pages by some specific FTL algorithm, so something like that. So I will just prepare some specific problems. So I will not ask about some your opinions, but so I will not ask about some content of the papers. But you need to understand some detailed some translation schemes, that means we learned during the previous classes. So it's okay, or okay. So I'll stop here. Okay, and then let's see during the exam. Okay, bye guys. So I will also post the detailed exam protocol on the Blackboard. Okay, bye.